Have you ever wondered how AI code reviewers actually work under the hood? Maybe not, because some people say we won't even need review tools anymore soon, that AI models will just become so good we won't even have to review code at all. Other folks argue you can just use a frontier LLM or use the same coding agent that wrote the code to also review it. Well, let me prove to you how wrong they are. In this video, I'll demonstrate 3 simple review systems that I built to compare the quality of their review and the impact on your token spend on just catching one single bug. And after that, I'll explain to you step by step how you can build your very own AI code review agent from scratch. So, let's get into it. First, let me show you the bug I'm using to test these review systems. I've got a simple e-commerce app here. Nothing crazy, just order processing, discounts, that kind of stuff. In this calculator.py, I added a new parameter to the calculate discount function, a minimum purchase threshold. Makes sense, right? Only apply the discount if the order hits a minimum amount. But there's a problem. The apply discount method still calls calculate discount with only 2 arguments. The function now expects 3, so that's a classic contract mismatch. This code will crash the moment somebody tries to apply a discount. And the interesting part, in the diff alone, you cannot really see this. The change file looks fine, the bug is in the caller. Let's go ahead and see how our review systems will handle this. System 1, diff-only. We literally just grab the git diff and send it to the LLM. Fast, cheap, but completely blind to anything outside of those change lines. System 2, full code base. We grab the diff and every single file in the project. The model sees everything, it likely finds the bug, but you're also burning through a hell lot of tokens, and the model might get lost in too much noise. I mean, just take a look at the folder size that we're ingesting here to find one single bug. System 3, smart context. This one mimics how a human reviewer actually thinks. We look at the diff, but then we ask ourselves, what else is affected by this change? What does this code call? We use analysis tools to trace the impact and grab just those files for the review. That's pretty much what we're doing here in code as well, feeding only the relevant information into the LLM. We'll dive into what exactly is happening here after we run the tests. All right, let's run these systems one by one, starting with diff-only. We've got multiple commands to choose from here. Let's go with mode diff-only, since that's the one we're trying to run. And here's the context we're feeding into the LLM. Now, I'm using ChatGPT 4o Mini for this. If you're using a different model, you might see different results. But I chose this one because it helps highlight the broader effects at much smaller scale. Okay, it came back with a bug. Let's see what it found. It points out to calculator.py, line 5, bug category contract mismatch. Great. Function signature changed without updating callers. The function calculate discount row takes an additional parameter min purchase, but all existing callers are not being updated. Great. So the LLM is smart enough to detect that inside the diff, there is no update to any caller function. But it's really just guessing that the callers probably haven't been updated. That's actually pretty good. Yet the problem is it doesn't really tell us anything about where in the code base we need to go and fix that. But on the positive side, this ran in 4 seconds and only consumed 517 input tokens and 116 output tokens. So it's kind of cost effective, but incomplete. Let's run the full code base now. You can see we're sending a lot of code in here. All right, we got 2 bugs back this time. First one, same as before, contract mismatch, function signature changed without updating callers. But now also it finds something else in the order.py. It's flagging the order class methods, saying the pricing calculations might not reflect the change to calculate discount. Well, the line number is still not correct though. So as a suggestion, it's telling us to review all instances where calculate discount is called and so on and so forth. So it's already a little bit better, but not quite there yet. Now, here on the other hand, it ran significantly longer and consumed 19,000 tokens. That's a very different cost profile than what we saw before. Now, finally, let's run the smart review. Here's the context it built, the impacted code, the changes, the relationships. We'll dive into how this works in just a moment. And look at that, much faster, much fewer input tokens, and it found the bug. Order.py line 44. Let's check. And this is exactly the line that we're looking for. Great, but how did it do that? To explain this, let's walk through the code step by step. I've set a couple breakpoints to get us started. The first thing we want to understand is which lines changed. We pass the git diff and find exactly the lines that were modified. Looking at the line changes, we see that calculator.py had lines 4 to 15 modified. Line 4 is the function signature, the definition line. This is going to become important later. Next, we want to identify the modified functions, so we use Python's abstract syntax tree module to walk the syntax tree and find which functions contain these changes. Looking at the changed symbols, we see calculate discount spans line 4 to 16, and our changes fall right within that range. We scan all Python files in the project and build a call graph, basically a map of who calls what. If we look at the CG variable, the return of the call graph function, which calls order.py, you can see that it calls calculate discount. So now we know exactly which files to check. Here's the key insight that makes this work. We don't just check if the function was modified, we also check if the signature itself was modified. So, was the definition changed? Looking at that, we can understand if there was a contract change. We see calculate discount in the set. The definition line was in our changed lines. This means so the function contract changed and any code calling this function might now be broken. Since calculate discount had a signature change, we find its callers. Looking at the impacted files, the system identified order.py as a file we need to include. This is the file that calls our change function. Now we're building the impact snippet, which is basically just the part of the code that we need because it contains all the information about the functions that should be grounding the LLM in understanding this error. Lastly, we generate the package for the LLM. We send a couple things. One, the git diff showing what changed in the function signature for calculator.py. And secondly, the call side from order.py. And here we see the context that we built. The git diff, the changed code, and finally the impacted code, which contains the contracts and call sides. In this case, we can see our code right here. Great, and there's the result. I hope you enjoyed this tutorial. Let me know what you want to learn about next in the comments. Also, a quick shout out to my colleague David Loker, our VP of AI here at CodeRabbit, for inspiring this video with his work. If you want to learn more about David, you should check out my latest podcast episode with him here. See you in the next one.